Okay, so we have our solid, our liquid, and our gas. What changes a solid to a liquid? What are we doing? We're adding energy. As we add energy, those molecules start to separate and move around more. Move around even more. So you are increasing the energy when you go from a solid to a liquid to a gas. Now what happens if we go from a gas to a liquid? What are we doing? Decreasing or removing energy. And we did that. We used that cold water in that tub. That was removing energy. So we actually went from a liquid to a gas back to almost a liquid. So in that transition from going from the gas towards the liquid, those water vapor molecules were coming closer together. So do you guys all have that?
Yes.
I'm going to switch. So we're going to step this out and show exactly what happened. So we're going to draw our can. The hole is on the top. And it's a can, and it looks fine. It's just empty, and it's sitting there. So what's going on? We have air molecules on the outside of the can. We have air molecules on the inside of the can. It's empty, and it's open. The can is just sitting there. It's not getting crushed. It's not exploding, imploding. Nothing's happening. It's in a state of equilibrium. It's stable. So I'm going to show that with arrows. We have the equal amount of pressure at every point surface on that can. Top, bottom, all over. So when I go to revisit these notes, I want to make sure I know what I'm looking at because I might forget. So I'm going to write myself a little note. I'm going to write that this is an open can. And it has the same pressure inside and outside. So it's equal. Whoops. There you go. So that's the first thing we did. We had our open can, and then we went and filled it with some hot water, about an inch, and we put it on a hot plate. So what that did is it removes this air inside the can. So N2, O2, argon, right? All those air molecules. It moved that up out of the can. And what replaced those air molecules was what? Water, what? Vapor. Vapor. Very good. So that's our next step. We're going to take that can after it's filled with water vapor, and we're going to have turned it upside down into water. So now what I have is I have water vapor inside the can. And I have air molecules still on the outside of the can. Air molecules have a different mass than water molecules. So there's a little bit of difference in pressure due to that. And then what's the important thing? What do we just do by putting it in water? What did we do to that opening? Seal the opening. And then what else did the water do? Think about temperature. Okay, so we sealed the opening. And cooled the water vapor inside the can. So what I want to note, because I might forget this later, is this is water vapor. Water. And the circles are air molecules. Okay? So we're going to go to the next thing that happened because of that. When you look at a gas going to a liquid, those molecules get closer together, right? As we remove energy. Is that true? Yeah. It is true. So we're going to draw our can now, and we're going to start to explain why the crush. Those water molecules, they're going to be coming closer together. So basically your can had, before you flipped it, a little bit of water, just a teeny tiny bit of water in there, and mostly water vapor. When we cooled that can, what happened is that water vapor starts to move close together, taking up less space. And it didn't necessarily make a column, but I'm going to just draw those. Water vapors coming in closer together. So you have the same amount of water vapor. It's just now dense. It's condensed into a smaller area. So now what's happened is we have this area here. If only inside the can was a teeny bit of water and water vapor, and all the water vapor moved to the inside of the can, what is that yellow area? Empty space. So the yellow is empty space, which creates a what? Vacuum. There you go. So we just created a vacuum. So inside the can, things are changing. Outside the can, nothing's changing. We still have air molecules. So let's draw our air molecules all around the can. So because outside the can you have all these air molecules, what is the pressure? The pressure hasn't changed outside the can. What is the pressure of the atmosphere at sea level? 14.7 pounds per square inch. Very good. 14.7 pounds per square inch. So if you take this can and draw square inches all around it, there's 14.7 pounds pressing in and at all those spots. Okay? So we're going to explain that. So we have the vacuum being created. What happened? First, the water vapor condenses. And creates a vacuum. Which allowed the air pressure outside the can to crush, it's an important word, the can. And it did that fast, didn't it? How many of you heard a popping sound when your can crushed? A lot of you. So when you're done with that one last drawing, I want you to draw what your can looked like after it crushed. Where's my can? So what you ended up with is your crushed can. What's important to note is that the pressure on the outside of the can was greater, and that's what crushed the can. So you can see on the string there's all different sizes of the can, or the amount of crushing happening, which is explained by the temperature variation and the condensing, how condensed the water vapor occurred inside the can. So the faster the condensing, the more severe the crush. So now what I want you to do is rewrite your notes into paragraph form, like you're explaining this to like a fourth grader. What happened? Complete sentences in paragraph form. What happened? So take all those drawings and the words and write those out in sentences, and I'm going to come by and check those sentences.